Hi, this screencast is about VSEPR theory, and VSEPR theory is a mnemonic to help you remember valence shell electron pair repulsion. So valence shell electron pair repulsion. And what this really means is this is our 3D shapes of molecules. Okay? What's going on in a molecule, for instance, if we take water and we draw its Lewis structure, H2O, we have some electrons, and molecules do not form in a flat dimension. They have electrons which are pushing against each other because they all have negative charges, and we have bonds that are made of electrons that are pushing against each other. So in fact, our molecules form a three-dimensional shape. So in water, we have electron pair here and electron pair here, and they take up space, as well as the electron pair here in these two bonds. So what is really going to happen when you have a water molecule is you are going to form a shape that is not a flat linear molecule, and that's what we're going to investigate in this screencast. All right, so here is our water molecule again. You can see that we have oxygen in the center, we have our two hydrogens, and these red dots, they represent the electrons. Okay, so we need to know some of the terminology. You can have a bonding pair of electrons, and you can have a non-bonding pair of electrons. In a bonding pair, these are the electrons that are shared between two elements. So these are shared between two elements. And these are in the form of a bond. Okay, and then you can have non-bonding electrons, and these are, for example, the red ones here. These are unshared pairs. So these electrons are free on one element, and they are not in a bond, and they are non-bonding electrons. They are also known as an unshared pair. For the remainder of the VSEPR theory, we're going to focus on how many bonding pairs and how many unshared pairs electrons we have in each molecule to decide what overall shape we will take on in the VSEPR theory. Okay, so there's a couple of steps when you're trying to determine what shape the overall molecule takes on. The first step is you need to draw the Lewis structure. If you don't have the Lewis structure, you really can't decide what shape the molecule would take on. So you need to have the Lewis structure drawn. Sometimes I'll give you the Lewis structure in a problem, and other times I'll just give you the formula, and you'll have to determine the Lewis structure from the number of electrons involved. The second step is to look at the central atom. Okay, so once you know what's in the middle, you need to look at what is attached to that central atom, and you'll need two things. You need to know how many bonds or how many things are bonded to it, and you're going to need to know how many lone pair electrons you have, or unshared electrons. So if we go back and we look at our example of the water molecule, which had our two hydrogens attached to it, and we had two lone pair electrons. In this example, we would say that there's one bond and two bonds, so that's two bonds, and we have one pair and two pairs. So this is two pair of electrons on it. So when we go on to decide what shape it takes on, we would look for the one that has two bonds and two pair of unshared electrons. Okay, so the first shape that we can have will have two things bonded to the center and no lone pairs. And what this looks like is that you will have a central atom with a bond on the left and a bond on the right. And as you can see in this crude drawing, it is in the shape that is a straight line. So this one is called linear. Now, one thing to keep in mind is that you can have a double bond on both sides, and that is still going to be linear because you have two things bonded. It's one thing, two things bonded, and no lone pairs. So there's no unshared electrons on the center atom. When you have that case, you have a linear atom. Now, let's move on to the second one. The second one is when you have three things bonded to the center, and no lone pair. So what that looks like is you have your center atom, you have a bond, and a third bond. And this one is called trigonal planar. This takes on a even spread of these three single atoms away from each other. The goal here is that these all have electrons around them, and the electrons all have negative charges. So they are repelling each other, and they are trying to be as far away from each other as possible. So the geometry that becomes is that you have three things evenly bonded, and you can kind of see that this angle, and this angle here are all about the same. They're all 120 degrees. Whereas up here, the angle was 180. Okay? So again, this second shape, trigonal planar, has three things bonded and no lone pairs. Sometimes when you have a trigonal planar atom, you can take one of the bonds away and change it to a lone pair. So this would be two things bonded and one lone pair. So what you become then is not trigonal planar. You change it up a little bit. You still have your center atom, and you have your two parts that are bonded, and in the center here, you would have a lone pair. Now, the bond angle is roughly the same, but the shape name is different. This one is called bent. This is when you have two things bonded to the center and one lone pair. Keep in mind, just like up here, when you could have a double bond, you can have a double bond here as well. It doesn't have to be on the left, it could be on the right. But remember, all the atoms need to have 8 electrons around them to fulfill the octet rule. So in order to do that, you would have a double bond. So you're looking for 2 atoms bonded to the center, and one lone pair would get you a bent. It is part of the family of trigonal planar, but it has a separate shape. Our next shape has 4 things bonded and no lone pairs. This one gets a little tricky to draw on a piece of paper, but we start with an atom in the center, and we have an atom attached on the top. Now around the bottom, we're going to evenly have 4 distributed. So if you can imagine with me, one of these 3 around the bottom is kind of pointing away from us, and one of them is kind of pointing towards us. Okay, so you have to think in 3 dimensions when you're looking at this picture. Now this one is called tetrahedral. It has 4 things bonded and no lone pairs. The bond angle here is roughly 109.5. And so these 4 are evenly distributed. Sometimes kids like to think that the bottom 3 here are kind of in, that this bottom 3 are kind of like in a tripod structure if you were actually building it. Okay. Now, if we take away one of these atoms that are connected to the center, and we leave the 3 on the bottom, we would have, and then replace it with a lone pair on the top, we would have 3 things bonded and 1 lone pair. Now, this one is called trigonal or triangular. Trigonal, we'll go with trigonal. Pyramidal. I have seen it in both sources, so I'll write it both ways. So triangular, pyramidal. The important part is pyramidal. Okay, and this has 3 things bonded and 1 lone pair. And the bond angle changes just a little bit. This one becomes 107.5. You don't need to memorize the bond angle. I'm just giving that to you so that you recognize that the angles are a little bit different. The reason is these electrons will push with a different strength than the bonds. So they push a little bit harder, causing the bonds to squeeze together. The electrons tend to take up a little bit more space than the bond pair. There's one more that is a branch of the tetrahedral, and it would have 2 things bonded and 2 lone pairs. So what you do is you have your center, and remember we had already replaced the top with a lone pair to make our triangular pyramidal. But now we are going to take away another bond from our original 4, and we're going to replace it with another pair of electrons. Now this one is called bent, and yes, I know there's already a bent. The difference is that one of the bents is from the trigonal planar family, and the other one is from the tetrahedral family. And it doesn't matter right now for what we're doing, whether you're meaning bent of this kind or bent of the other kind, as long as you know what's going on. So this one has 2 bonds on the center and 2 lone pairs. And you can see that the angle is a little bit different, and depending on which orientation you rotate this particular model to, you're going to see your bond angle is something in the neighborhood of 104 degrees. Alright, so the last 2 models that we're going to address in this screencast are both, they are expanded octets. So they are exceptions, expanded octet. So these are exceptions. And in these cases, we're not going to follow the octet rule completely. And then remember, the octet rule says that we have to have 8 electrons. In the expanded octet, we're going to have 10 electrons or 12 electrons, depending on which shape we're drawing. So in the first case, we are going to have 5 things bonded to the center and no lone pair. And in this drawing, you have your center atom, and you start with a linear, but around the center you're going to have 3 molecules drawn evenly. So if you imagine with me, you have your straight up and down, and then around the center you kind of have a trigonal planar. So you have bond angles of 2 different choices. You have a 90 here, and then here is a 120. So depending on whether you are in the axial position or the equatorial, you have a different bond angle. Now, the axial would be the up and down, and the equatorial would be around the center, around the equator, just like on the Earth. And so this one is called triangular bipyramidal. Triangular bipyramidal. And it has 5 things bonded to the center and no lone pair. Okay, so I mentioned that this was an expanded octet. This one has 10 electrons around the center. Each bond counts for 2 electrons, so if you count around it, you have 5 things bonded at 2 electrons each. That would be 10 electrons. Okay, so in our last shape, we're going to have 6 things bonded to it and 0 lone pairs. And this one is going to have the 12 electrons around it. We're going to start with our center atom, and we're going to have our linear. And now around the center, we are going to have 4 things evenly connected. And this one also is a little hard to visualize, but we're going to try. And this one is called octahedral. So, again, you have an axial and an equatorial position. You have, this is your axis here, so that's your axial. And then your equatorial, and this one is these 4 around the middle here. Now, the one thing that's different in this shape is that these are all 90 degrees. So it doesn't matter what position you're in, they're all going to be 90 degrees. There are 6 things equally distributed around the middle. You have 1, 2 on the top and the bottom, and then 4 around the middle. Again, this is expanded. You have 12 electrons involved in this shape. Only specific elements can take on 10 or 12 electrons. Not every single element can. So what you need to do when you're deciding what shape your molecule actually takes on is you have to draw the Lewis structure and then look at the center, deciding how many bonds and lone pairs you have, and that will allow you to predict the shape.